All right, hi guys. Today we're going to be talking about plate boundaries, and I want to start with your reference table on page 5. If you look at page 5 of your reference table, you'll see all these different plates across the globe, and all their edges are bounded by different types of plate boundaries. And the plate boundaries, the key on the bottom shows you the different types. So you'll see at the bottom it says the relative motion, so which way they're moving. You have a transform plate boundary, a divergent plate boundary, and a convergent plate boundary. And what we're going to do in these notes is essentially just talk about these different types of boundaries. So I want to start with this picture over here, which is cool because it shows all of those boundaries all put together into one image. So you can see on the screen there is a plate boundary called a divergent plate boundary, which is located right over here. Okay, on the screen you can see the arrows separating from each other. You can see over here these two plates are colliding. This one's going this way, this one's going that way. So that's a convergent plate boundary. And then also in the background over here, you can kind of just make out that there's a plate over here that's sliding past the other one. That's a transform boundary. So let's take a look at these individually and jot down some notes. Now I've handed these notes out in class. You can print them at home and you can just copy along with me. So let's start with a divergent plate boundary. What exactly is a divergent plate boundary? Well, it's essentially where two plates are separating, so it's spreading apart. Okay, we'll kind of leave it simple like that. Two plates separating from each other or spreading apart. That's what divergent means. Now on your reference table, you're going to see a line and you're going to see arrows that essentially point opposite ways, separating from the middle. So we have this divergence and therefore spreading. And there's two different examples of divergent plate boundaries. Most divergent plate boundaries are oceanic, meaning that they occur or are found in the middle of the ocean. And where you have that, you typically have a mid-ocean ridge, which you can see in this diagram on the screen. So there's a mid-ocean ridge right here along this line. Occasionally you might get some volcanic activity associated with that. But we have this spreading apart, and you can see an arrow going that way and that way separating from each other. Why? Well, it all has to do with this movement of material in what's called the asthenosphere, which we'll get to at the end of this. But they're both separating and spreading apart on either side, and therefore you get this spreading boundary. Now, a good classic example of an oceanic spreading center would be the Mid-Atlantic Ridge, which we've been talking about a lot because we talked about Pangea and seafloor spreading and Hairy Hess and all that. So the Mid-Atlantic Ridge, that's a great oceanic example. A good continental example where this is happening on a continent, where the continent is separating, is actually located in Africa, called the East African Rift. And we'll take a look at both of those. Let's start with the reference table. So let's go back to the reference table. And if you look at your reference table, let's start with the Mid-Atlantic Ridge right here. You'll see on the screen the Mid-Atlantic Ridge is right here, goes down the middle. And on either side of that, we have arrows separating from each other. And this goes all the way down the Atlantic, again, separating from each other, spreading these plates apart, South America and Africa, North America and Eurasia. Okay, now let's take a look at the East African Rift, which is on the left-hand side of your map. You can see there's a line that kind of goes down the middle here. And on either side, the arrows are spreading apart, which basically means that this part of Africa right here is all going to separate from the rest of Africa. So it's going to diverge or spread apart and eventually separate. And right down the middle here, in this region, there's a lot of lakes and waterfalls. Some of the biggest Victoria Falls is in this region of Africa. Very, very pretty country. Let's actually take a look at that. I have some pictures of the East African Rift right here. So you can see where this is happening on the eastern side of Africa, Lake Victoria. You can see in this picture, I've put some arrows on here just to kind of indicate the motion. You can see this valley here, and in that valley we have separation on either side over here, going that way and that way. And in this picture up above, you can see there's new material that's formed in the middle here, separating the continent apart, okay, on either side. So that's what we call a divergent plate boundary. Okay, and just another example that's interesting, I'll just show you this. This is Iceland. Iceland is right on the mid-Atlantic ridge, as you can see in this picture, and you can see it spreading apart on either side. Volcanic activity is happening in the middle, and so you actually have the formation of new material on Iceland and separation there. Pretty cool place to visit. Now, let's take a look at our next example of a plate boundary called a convergent plate boundary. So a convergent plate boundary is just the opposite of a divergent. We have two plates colliding, okay? Colliding plates, running into each other, smashing together. And there's three different examples of colliding plates or convergent plate boundaries, and you can see them listed on the next couple of pages. We have what's called an oceanic continental example, an oceanic example, and a continental example. Let's start with the one that's pictured here on the screen. We have two plates. One of them is oceanic, this one right here, and it's colliding with this one over here, which is a continent. And as they run into each other, the oceanic crust, as you can see here, is going down. Another word for that going down is subduction. I'm just going to write that on the side here. Subducting plate, subduction. Okay, that's what's happening here. Now, why do you think this is sinking? Think about that for a second. The reason the oceanic plate is sinking is because it is more dense. I'm just going to write that over here in green. More dense. Okay, the oceanic crust is made from basalt. Basalt has a density that's greater than the continental crust, which is less dense. I'm just going to write that off to the side here, less dense. Okay, and therefore, because it's more dense, it sinks. Now, as it sinks, it's eventually going to get pressurized, so you have a whole bunch of stuff going on here, a lot of metamorphic rocks. You have some melting going on here, so you have magma formation, which rises to the surface, and you get all these volcanic mountains along this border. All right, so right along this, essentially this whole mountain range here is a lot of volcanoes. Now, another thing to take note of, another geographic feature, are trenches right off the coastline. As this pulls down, it creates an ocean floor that's deeper, and therefore we call that an oceanic trench. Great example of this is located off the west coast of South America. We call it the Peru-Chile Trench, and that is part of, it's off the coast, but it makes up the Andes Mountains as well. The Andes mountain chain goes all the way down the west coast of South America. And if you want to take a look at that, let's look at your reference table. It's located right over here. And you can see in our picture we have a collision. Let me use red. Okay, a collision between the two plates. And you have this Peru-Chile Trench. And then all these mountains are located, the Andes Mountains are right up the west coast like that. Okay, so that's a oceanic and continental collision. The Nazca plate, as you can see on the screen here, is oceanic, and the South American plate is continental. Okay, now let's take a look at our next example. Our next example is what we call a oceanic convergent plate boundary. And with an oceanic convergent plate boundary, we have this collision, but it's interesting because they're both oceanic crust, which means they're both very dense. They both want to sink. They both want to go down. One of them will eventually, because it's probably the smaller one, and it will sink down and melt, and we'll have the formation of, this magma and then these volcanoes that are located right along here. We call this a volcanic island arc. So you have a whole bunch of volcanoes in the middle of the ocean. Also associated with this is a very deep trench. Because both of these plates want to go down in this region, we have a very deep part of the ocean. Great example of this is out in the Pacific Ocean called the Mariana Trench. Okay, another good one is the Tonga Trench, which is also out there in the Pacific Ocean. The collision of two plates that are both oceanic, they both want to sink. And you can take a look at that on your reference table. Okay, in fact, let's just go there really quickly. Here we go. We have the Tonga Trench and the Marianas Trench, and you can see it's a convergent boundary. And if I just highlight the Tonga Trench, there it is, the Pacific Plate and the Indian Australian. Marianas Trench is the Pacific Plate and the Philippine Plate colliding with each other. And along this border, you also have a bunch of islands. The Tonga Islands, the Marianas Islands, they're all out there. Okay, our last example of a convergent boundary is what we call a continental-continental collision. And when we have this happening, we have two plates that are both colliding. They're both continental, which means they both want to stay up. They don't want to sink. They want to rise because they're both less dense. And so it just kind of slides underneath the other one without really sinking and melting. And so what you get is a whole bunch of mountains, folded mountains that are really, really tall, very big, huge mountains that are bigger than any in the world. So you can think of a great example of that would be the Himalayas. The Himalayan mountains, okay, including like Mount Everest, which is the tallest in the world, are created by this collision between India and Asia. So let's take a look at that on your reference table. It's located right over here. Okay, so there's India, as you can see right over here, okay, and it's colliding with Eurasia here. And so you have these really big mountains, the Himalayas, in this region of China and India and Nepal, okay? Now, that's our convergent boundaries. Remember, there are three different types of those. The last type of plate boundary is what we call a transform boundary. So let's take a look at a transform boundary. Transform boundary happens when two plates slide past each other. I'm just going to write that off to the top here. Slide past each other. And therefore, there's no collision, there's no divergence, there's really no volcanic activity associated with this because we don't have any sinking and melting. We don't have any large mountains. We don't have any trenches. It's mostly just a calm sliding past, but as a result, we get these fault lines, and you can see that on the picture right there. There's a fault line here where a lot of earthquakes will happen. So earthquakes like crazy along these boundaries because you have all this tension building up as they slide past each other. So sliding that way, sliding that way. Great example of this, the San Andreas Fault, which you probably are familiar with because it's out in California. A lot of earthquakes associated with that. And that is our last type of plate boundary. Now, why do we have all these plates moving around, colliding, diverging, etc.? Well, all has to do with what's going on down below the crust, and that is a process called convection. So I'm going to write in the notes here, convection, and specifically convection in the mantle, that's the layer below the lithosphere, is the driving force behind plate tectonics. And what you have is hot material that's less dense will rise to the surface, and then when it gets to the surface, it will cool off, and it will become more dense, and it will sink back down again. This causes a convective flow or convection that is going to essentially move the plates, moves the lithospheric plates across the surface of the Earth. So if I were to draw that into this picture, this top layer right here is the crust, and you have material that this is like the core of the Earth. This is the mantle of the Earth, okay? And we have material that rises up and then is going to spread apart on either side, okay? This is a divergent boundary, so divergent here. And it's spreading apart, so driving this that way and that way. Then it comes over here and it gets cooler and it will sink back down again. I'm going to change the color to blue because it's cooling off. And it sinks back down again over here. This plate over here is colliding with it. Okay, and where it's colliding, we have a convergent boundary. Convergent here, convergent here. And that collision causes subduction, and eventually this cycle starts all over again on either side. And so you get this big, huge convection current, which you can see happening right in here and right in here going that way. So that divergent and convergent boundary is all due to this convection within the mantle, okay? And just to show you some other pictures that are associated with that, there's different theories for how this occurs. This is called split mantle convection, but you can see all the motion going on here. You can see the ridge located right over here, okay? And on either side, it's spreading apart, separating. And then where you have a convergent boundary here, they're sinking back down again. Same is true with this other picture over here, which shows the same thing as this whole mantle convection. Same idea, generally speaking. Okay, so that's plate boundaries. That's the big message behind them. The big thing is being able to use your reference table on page 5, being able to use the key to identify different plate boundaries and the motion associated with them. And that's pretty much it. If you have any questions about anything, just let me know.